Okay. I taught this over 2 days. In reality, it's only worth 1 day. Okay. This is a lesson that could have been tied on to Unit 6. You guys remember what Unit 6 was all about? The first unit we did in the second semester. Antiderivative. Since the second semester started, that's when we've done the antiderivative. So like, what we're about to learn is less conceptual and more procedural. We are just going to take more antiderivatives of special functions where we will use a technique called U-Substitution. And this technique will help us undo the chain rule. We've already been undoing the chain rule. In Unit 6, like one of the lessons was, how do you take the antiderivative of cos 3x plus 2? And the key to knowing how to do this is to knowing how to take derivatives. If you know how to take the derivative, you should be able to understand what is necessary when we undo things. When we take the derivative of cosine, we get negative sine. When we take the derivative of 3x plus 2, we get 3. The chain rule says multiply these two together. And you get negative 3 sine. What starts in the inside stays in the inside. Okay. Same here. This is a different example. Remember, the derivative of log is 1 over, or something to the negative first power. So this would be 1 over what starts in the parentheses stays in the parentheses times 2. Maybe doing this one. E to the 5x plus 6, e to the power is the outside, the power is the inside. If we remember the chain rule, that's going to be extremely helpful if we're undoing the chain rule. Okay? So, which far away, I'll do it later. When we go backwards, one thing we notice with the chain rule is like whatever started in the inside stayed on the inside. So when we go backwards and we take an antiderivative, the stuff on the inside is going to stay on the inside. But we're going to take the antiderivative of the outside. The antiderivative of cosine is positive sign. We include a plus c. But since I know what will happen if I take this derivative, I realize this isn't the answer and I need something else. A 1 over 3. I need this 1 over 3 because when I take this derivative, I get cosine of my stuff. But then the derivative of my stuff includes a 3. I need the 1/3 to cancel with the 3, so I just have what I start with. So we've done this before. This one, we'd probably start out by writing as 2x plus 3 to the negative first. Realize that the power rule doesn't work, that the antiderivative of a negative first power is a log. So log, what starts in the inside stays in the inside. But to undo things, we need a 1/2 because the derivative of the inside is 2, and I don't see a 2 here. What starts on the inside is going to stay in the inside. The antiderivative of e to a power is e to the power. So I start with this, I think about the derivative, and I'm like, well, the derivative of this is going to have a 5 because the derivative of the inside. I don't have a 5 here, which is why I need a 1/5. Cool? If this is in our brain, we'll be able to do the more complex ones we're about to do and understand why we get the answer of what we get. Okay? So, this is a review from Unit 6. The easy undoing of the chain rule. Why don't we just start with F prime here, just for easy purposes so that we don't use big F. If you have a composition and it's just x to the first power, we can take the antiderivative of the outside, leave the inside alone. The antiderivative of F prime is F. But we need to undo the derivative of the inside. We need this 1 over x. Okay? All right, now we are going to see things that look a lot more complicated. It looks like this is a product. This is a product. This is a product. This is a quotient. So it looks like Mr. Messer is about to introduce me to a product or a quotient rule for antiderivative. Doesn't exist. Doesn't exist. It wouldn't be nice, right? But what we are going to realize is that this antiderivative is just like these antiderivatives. We will be able to, and you will eventually be able to do this by just looking at it, but I'm going to show you a technique to get this answer. We will be able to realize that, like, oh, this is like a form of the derivative of this. I'm going to call this G prime and this G. Okay? And that's important. That's going to enable us to undo what essentially is a derivative that came from the chain rule. I will be able to take the antiderivative of the outside and leave the inside alone. And if I understand the chain rule, I'll understand what else I need here. Now, I didn't include a 1/4. I didn't really take the antiderivative of the outside. I just turned this to a 4th power because I know when I take the derivative of the 4th power, I'm going to get 3rd power. Cool? Now, let's think about the derivative of this. I'm going to have the derivative of the outside, 4 stuff cubed, but then I'll have the derivative of the inside. Now, when I take the derivative of the inside, I get 3x squared. Oh, hold on, I have an x squared right here. So that's actually something that makes sense having. But what I don't have is a 4, and this derivative has a 3. I don't have a 12. You don't see 12x squared. What you just see is 1x squared. So what do? I put a 1/12 there. Now, if that doesn't make sense right now, I'm going to show you a very formulaic step-by-step technique to get this answer. It's going to be the first example we do. And maybe you use that technique until you kind of understand and be able to just go right here. The derivative of the outside, the 4 will come down. This turns into a 1/3. But then the derivative of the inside is going to be a 3x squared. The 3 and the 1/3 will cancel, leaving me with x squared. If you took the derivative of this, you get that. If you don't get that, it's okay. I'm going to show you a technique. This one down here is actually pretty easy. The inside is going to stay the same. I'm going to take the antiderivative of this outside, and it's negative cosine. I'm not going to pay attention to this x cubed because I'm going to start with this and I'm going to think about if I took the derivative of this, what do I get? Well, I'd have the derivative of the outside, which is positive sign, and then times the derivative of this x to the 4th. The derivative of this x 4th is 4x cubed. I don't have 4x cubed, I just have x cubed. So what do I need? A 1/4. If you don't understand that, I will show you a step-by-step approach to get that. Where it can get really complicated to do just by looking at it is when we have like fractions. But I'll show you how you could do it. And this one's tricky. This is a 1/2 power. I'll take the antiderivative of the outside. I get 3/2. If I thought about taking the derivative of this, a 3/2 would come in front, and a negative 2x would come in front, giving me a total of like a negative 6x in front. The 3/2 and the 2x. So 3/2 and negative 2x. That's not negative 6, negative 3. So a negative 3x would come in front. Oh, I have a positive 3x, which means what I just need is a negative sign. You don't understand that? That's okay. A lot of people love this lesson because it's back to being less conceptual and more procedural. What I'm kind of doing is using a concept to get this antiderivative. I'm about to show you how to get these antiderivatives in a procedural way. It's intense though. I'm warning you. There's a lot of steps to it. Some of you, if you understand this and this and this, you might be like, yeah, I'm not going to use it unless I really have to. And you will all have to use this procedural method at some point. So everybody has to learn it. But for a lot of questions, you can skip it. What we are going to be doing is taking the derivative of this and going backwards. We are going to be taking antiderivatives of something that starts like this, and we will turn it back into the original chain, which is what we've been doing. Okay? And here's how we're going to do it. Now, of course, first things first, I should have mentioned this. What does this mean to you? Antiderivative. Can you type this into a calculator? No. Why can't you? It doesn't have numbers. The calculator doesn't think of that as an antiderivative. The calculator with numbers thinks, oh, I'm going to accumulate using some sort of Riemann sum these y's times x's, right? So you are not allowed to type in just an integral into your calculator because your calculator doesn't know how to take antiderivatives, okay? So like for the first half of this lesson, like you can't even use a calculator to check. Second half of the lesson, we can use our calculator to check because we will have them, okay? So let me show you the step-by-step approach of how we get our answers. This answer is f of g of x plus c. This answer was 1/12 x cubed plus 3 to the 4th plus c. I showed you how to get this answer, thinking of this as being, oh, this is a change derivative. I can undo the outside, leave the inside alone. Realize what the derivative of the inside would be able to put something in front so that's going to get rid of what I'm going to have, okay? All right, and here's the step-by-step approach. It's called U-Substitution. Mathematicians like to use U when substituting. Why? I don't know. They just choose U, okay? Here you go. Step 1, we will identify the inside of the composition. And we will do some work on the side. So to the right, we're doing some side work. We are going to say U equals that inside of the composition. Here's just a more conceptual using notation. Here is an actual example, which we already know the answer for. Okay. We will take the derivative of this. Now, this is tricky because it's like, take the derivative, Mr. Messner, you're telling me that we're supposed to take an antiderivative. Yes, but this is going to be part of the process to undo things and to be able to take an antiderivative. Now, when we take the derivative, I want it to be in a very specific looking notation. It's called like a partial derivative notation. The way I kind of show you, and don't write this down, is if you took the derivative of this, You don't get u prime. Let's write it as du dx. Again, don't write this down. Du dx equals 3x squared. What I'm going to want to write is the partial derivative notation, which is du equals 3x squared dx. This is where it comes from. It's like du dx. I multiply both sides by dx. I get this. So you're taking the derivative, but you're going to be using notation that is a little bit different. But there's reasons behind it that you will see in a second. So I'm going to write this as du equals g prime dx. I'm going to write this as du equals 3x squared dx. Again, we're still working on the side. We will solve this for dx, typically by dividing or multiplying by 1 over g prime. I like to write it as 1 over g prime du equals dx. Keeping things, dx stays on this side, du stays on this side, the g prime moves. Here, 1 over 3x squared du equals dx. All this work that we've done was for a reason, though. And the reasoning behind this is the next step, the substitution step. We will take the work on the side and we will substitute in u. So the start of our work we'll substitute in, and the end of our work we'll substitute in. There's a reason why this dx is there. It represents, like, with respect to x or a small change in x, like, it needs to be there because we're going to replace it with what it's equal to. Okay, and again, this is just a formulaic process. After you've done it a couple times, it's not that bad. Don't get too overwhelmed by it right now. Now, everything else is going to stay the same. But this turns into u, but f prime stays. G prime staying. Dx is replaced by 1 over g prime of x du. Let's see what that looks like over here. X squared stays. The parentheses stay. This x cubed plus 3 turns into a u. Dx turns into 1 over 3x squared du. Now, the purpose of this is to understand, like, why we need a 1/3. Like, where did this 1/12 come from? It came from the fact that we're going to have a 4 and a 3 when we take the derivative of this. This 4 will come down, and the derivative of the inside will have a 3. There's that 3. Now, if all was right in the world and we're doing this correct, stuff is going to cancel. X's are going to go away, and you're just going to be left with u's. So now I just have f prime of u du, and this is 1/3 u cubed du. We now have something that is a lot easier to look at, that you can take the antiderivative of normally. The antiderivative of u to the third is u to the fourth times 1/4. The 1/4 and the 1/3 now can combine to be 1/12, u to the fourth plus c. Do you see how that then can turn into 1/12 x cubed plus 3 to the fourth plus c? This step-by-step method got us the 1/12 that we kind of conceptually got through our understanding of the chain rule. Here, you take the antiderivative of f prime, you get f. Sorry. When you take the antiderivative, the du goes away. When you take the antiderivative, the du disappears. It's like you took the antiderivative with respect to u, so du is gone. You just get f of u plus c, and then Boom. You can turn that into f of g of x plus 2. We got there. Did it take us a while? Is it intense? Yeah. Yes. One. The antiderivative of like dx is just 1, or it's just x. Yes, but it doesn't mean this. It's taking the antiderivative of this with respect to u. When I take the antiderivative of this with respect to u, I get this. Yep. A lot of people get tripped up on like, where does the du go? It's like, well, it's like, it just goes. We took the antiderivative with respect to u, we took the antiderivative with respect to x, it's gone. Okay? We already know the answer to this. This one was tougher to get conceptually. I took the antiderivative of the outside, I had a 3/2. Thinking about the derivative of this, the 3/2 comes down and a negative 2x comes down. The 2's will cancel, leaves me with negative 3x. I have positive 3x, which is why I realize I just need a negative here. If you are not comfortable with that, this is your method. Ready? Step 1, set u equal to the inside of the composition. Step 2, take the derivative of both sides, but leave it in interesting notation. du equals negative 2x dx. Step 3, solve for dx. Get dx by itself. You'll have 1 over negative 2x du equals dx. This is work done on the side to enable us to do the U-substitution step. Sub in the beginning, sub in the end. Rewrite this integral using that stuff. Everything else stays the same. That just stays. It's going to take care of itself. This process will take care of everything. We will get this answer without having to think much, just by like doing this process. Now the x's will cancel, and I'm going to rewrite this so it's negative 3/2. Square root u, I don't like to take the antiderivative of that. I like to turn that into a 1/2 power, and I get that. So this is just me rewriting. Now, I am ready to take the antiderivative. This is a step that a lot of people forget if they use this technique, is they forget, like, what's our purpose here? To take an antiderivative. So this turns into u to the 3/2. I add 1. I multiply by the reciprocal 2/3. I can combine that with a negative 3/2. The du is gone. The integral is gone. I've taken the antiderivative. I have a plus c. What happens? The 3/2, the 2/3 goes away. Just leaves me with the negative. I get negative u to the 3/2 plus c. Do you see how we get that answer on a step-by-step way? Maybe, maybe not. Okay. How do I do it? 9 minus x squared gets plugged back in for you. There it is. All right, let's see if you can, because we've already done this one. I know what the answer is. Yeah. The power rule. If I'm taking the antiderivative of something to a power, you add 1. you multiply by the reciprocal. If this is 1/2, you add 1. When you add 1 to 1/2, it's 3/2. Add 2/2 to 1/2, you get 3/2. Multiply by the reciprocal, 2/3. See if you can take the antiderivative of this. Understanding that that is like, that comes from a chain rules derivative. Understand the inside and the outside of a composition. Understand that this is coming from the derivative of the inside. See if you can do it. Either conceptually, understanding the chain rule, or using the U-Substitution method. I already got the answer to this. Let's see if you can get the answer to this. First thing, what starts in the parentheses stays in the parentheses, so that's going to stay there. Insides of compositions always stay. Don't take the antiderivative of the inside of a composition. It's just like, it just stays there. I'm going to see sine x to the 4th is the composition. I'm going to take the antiderivative of the outside of the composition. I get negative cosine. I think about the derivative of this. And it's going to be positive sine x to the 4th, but then times 4x cubed. Oh, there's an x cubed. I don't want the 4, which is why I need a 1/4. If you got that, great. If you didn't, here we go. U equals the inside of the composition. Du equals 4x cubed dx. Dx equals, 1/4x cubed du equals dx. Substitute. There's that 1/4. 1/4 shows up using this step-by-step approach rather than using our brains and our understanding of things. Everything stays the same. You find that x's will cancel. There's that 1/4. I will take the antiderivative, the integral, the du will go away, but I have to take the antiderivative. The antiderivative of positive sine is negative cosine. And then I finish things off by replacing what u is equal to. What do you think? Who likes figuring it out themselves? Raise your hand. Who likes just like looking at this and then figuring out and getting the answer? Who likes the U-Substitution method? See, there's both. There's both, and that's okay. However, the guys who just figured it out, you will be forced to use this method. I'll show you. No, because there will be specific questions that force you to use this method. And these questions arise when we start throwing numbers in here. These questions arise when we don't have functions, but we do have notation. Okay? So, if you can figure it out, a majority of the questions you're going to be fine for. But there are some questions where you still have to kind of understand this technique and use it. Now, we are going to get there. But we got a lot of other stuff to do. I'm going back to where we were. I'm just showing you, you didn't have to flip around. Since we have enough time, we can get through everything. Well, maybe. We have 20 minutes. Okay. Ready? I now have boundaries. I now could plug this into my calculator and get a numerical answer. That's great, right? Oh, you won't have a calculator for this question, but at least we'll be able to check Okay? Now, if we wanted to, we could take the antiderivative of this and then plug in 0 and 2. Okay. Inside stays on the inside, just like always. This 1/2 power, I'll take the antiderivative of I got a 3/2. If I took the derivative of this, I'm going to have a 3/2, but I'm also going to have a 2x, which means I'm going to have a 3x. I don't want 3x, I just want 1x. I need a 1/3. Don't love this example, but plugging in 0 and 2, I get 4, 5, 6 to the 3/2 times 1/3, minus plugging in 0. Unfortunately, I don't get 0. I get 2 to the 3/2 times 1/3. Since my calculator now can help me, my calculator can accumulate using a Riemann sum type approach. It will accumulate that function from 0 to 2. It gives me this answer. 3.956 is 1/3 times 6 to the 3/2. Thank you. You guys are all over it. Minus 1/3 times 2 to the 3/2. I know, me too, but it'll divide first and then it'll multiply. This won't be in the bottom. It's going to be fine. Yeah, we'll do the exponent, sure. This is simplified. That's simplified. That's the answer. Okay? Now, if you didn't get this, if you're a U-Substitution person, now this is when all of you non-U-Substitution people need to pay attention, because I'm about to show you something that's very, very important, where you're going to be tested on this. Okay? Now this is where we start. This is the work on the side. Here's the key, guys, for all of you non-U-Sub lovers. Not this. This is all fine. The numbers that go here and here are not 0 and 2. Okay? Here's the reason behind this. We are summing up height times width. This width is a delta x. These are x's. If we change dx to du, this represents a width or a change of u. I need u. This change of bases, which requires you to change your boundaries, is required knowledge for everybody. I have x's, but I need u's. How do I change x's to u's? I have connected my x's to my u's using u equals x squared plus 2. You can use u equals x squared plus 2, plugging in your x's, you get u's 2. Plugging in your x's, you get u's 6. Now, 2 and 6 don't seem like familiar numbers to me. Oh, 6 and 2. Watch what happens. If I rewrite this as 2, 6, 1/2 u to the 1/2, if I take the antiderivative, I get u to the 3/2 times 2/3. The 2/3 and the 1/2 cancel. Boom, I get that 1/3. Should have put plus c here, but we know it's going to go away. Watch this. We didn't have to go back to x's. We could have stayed with u's. And if you plug in 6 and 2, you're going to get that same answer. Now, a lot of you are thinking, okay, Mr. Messner, but couldn't I just change it back into x's and get the right answer? Yes, sure. Except I'm going to ask you a question. Like this. This is a question you'll see on the test. Question that's often seen on the AP exam. Where they said, hey, here's an integral. I would like you to rewrite this like this and tell me what number goes here, what number goes here, and what number goes here. There'll be like an A, B, C, D, all with different numbers. And you got to pick the right one based on the numbers. So you are forced to use U-substitution. You are forced to change your bases and your boundaries. And you're not even asked to take an antiderivative. You're just going to rewrite this in terms of f of u and du. So if you've been like, I'm not paying attention to all this garbage, this is so much work, I can just get the answer. Well, time to start paying attention to the garbage. I know who you are out there. Okay, figure it out. Everybody. The 6 plays a factor. No. The 6 plays a factor in the answer. 6 is not this number. I'll tell you that. Now, many of you will understand that u equals 2x. Embrace this, guys. Don't give up. This is 8 and 18. Great. If you have been using U-substitution, you know it doesn't just stop there. You have to take the derivative. You have to solve. 1 over 2x du equals dx. You have to substitute in. This turns into f of u times 1/2 du. This still equals 6 for now. And yes, you do change your boundaries because you change your bases. Your boundaries change to 8 and 18. But look at this guy here. Multiply both sides by 2. You can multiply everything by 2. Yeah.
So whatever number you get on the outside of your fraction, flip it and multiply everything by that.
I don't want to say that. I'm not sure if it's going to be true. Look at your homework. All right, let's pull out your homework real quick. Flip to the last page. Euler. Rewrite this one. Everybody, let's practice. Rewrite this one as an integral of f of u du, where you figure out what this number is, what this number is, and what this number is. This is the last page of your homework, the bottom right one. No. You're staying here.
With the one that was 0 and 2, was the 0 stay 0 or just something else?
If u was 2x, that would stay 0. Yeah, do this problem. This is good practice. This is practice changing your bases, changing your boundaries. Yes, it's very formulaic. It's very like derivative rules.
Is this not it? I feel like this should be it, right?
What'd you get, 94? 24. I think that ends up being it.
Right? You don't even use the U-Substitution. You just,
Good.
like you normally do
Well,
it
good.
and put the number and then just take the inverse and multiply everything by the inverse.
Good. Then you're good. Some people are not going to do that.
Yeah.
Okay. Now, what's helpful here is that I do change my boundaries, but using x's, since with x to the fourth, stay the same. So this might not have been a good example.
Yeah, I was gonna say.
Sorry.
Okay.
All right. This is x cubed f of u, 1 over 4x cubed du equals 6. The x cubes go away. I get rid of the 1/4 by multiplying everything by 4. And yes, we do change our boundaries, but they don't change in their numerical value. If you can figure it out, good. Yeah, it's still 0 to 1.
Oh, it's still 0 to 1.
Because it's x to the 4th. And 1 to the 4th is just 1. Yeah. I don't flip it. There's an integral property. Okay. There's an integral property that says if you have a constant, you can just pull out the constant. And if I don't want a constant in here, I just want f of u du, and this is equal to a number, I will multiply both sides of the equation.
Wait, so when does the range, what is it called? The two numbers in the integral, when do those change?
They change when it's like 2x, 4 to 9. This turns into 8 and 18.
Yeah.
So,
how come it doesn't change here?
because it's 0 to 1 and it's
Oh,
u equals x to the 4th.
It's not 1/4 x. It's 1/4 x.
No, it's u equals x to the 4th.
Yeah.
All right. That's the answer. Yep. No, we got to move on. All right, team.
I'll figure it out.
Powers of E. You can figure this out. This is the composition. This is back on the notes. I'm sorry for going to the homework to show an example. What starts in the parentheses stays in the parentheses. We're just like down a question or two from where we left off. Okay. What starts inside the parentheses stays inside the parentheses. I take the antiderivative of e to the power. The antiderivative of e to the power is e to the power. So like, I'm starting off with this. If I took the derivative of this, I'd have e to the x cubed plus 2 times 3x squared. I don't want 3x squared. I just want x squared. I need a third. If you can figure that out, hooray. You're done. Plug in 0 and 1, and you win. Let's say you haven't been able to figure that out so far. Well, here's what you would handle, how you would handle powers of e. Set u equal to the power of e. du equals 3x squared dx. There's that 1/3. It's going to show up once we U-Substitute. Now watch, Dorler. Be ready. Changing bases means change boundaries. I change a base of dx, x's to du. Boundaries change to 2 to 3. Why? Because I plugged in 0 and 1 into this. Is it important if you just get the right answer? No, but it is something that you need to know because there will be certain questions requiring you to know that. The x squareds cancel. I can take the antiderivative of 1/3 e to the u. It's 1/3 e to the u. I could plug in 2 and 3 into this. It gives me the same thing as if I plug in 0 and 1 into this. 1/3 e cubed minus 1/3 e squared is the answer.
We don't want to pick up the coefficients like that? Wait, oh.
I mean, you can pull out the 1/3 and say it's 1/3 e cubed minus e squared, but you can't simplify e cubed and e squared.
Yeah.
Okay? There's one other thing that you have to see. Is that, and you will be tested on this, you will see something that looks like a composition. You will attempt to undo the outside and undo the derivative of the inside. And you'd be like, oh, well, the derivative of the inside is 2x. So, like, I'm going to have a 3 and I'm going to have a 2x. That's 6x. I guess I need to divide by 1 over 6x. Wrong. Why? Because if you had to take the derivative of this, you'd use the product rule, not the chain rule. This is not something that actually comes from the derivative of a chain. In fact, to take the antiderivative of this, you need to simplify. Don't assume, just because it looks like a composition, that you need to think about undoing the chain rule. If there was an x here, then you could do it. If there was an x there, you could undo this using the chain rule. Since there isn't an x there, you can't. This guy looks like it's a composition. Nope, just simplify. But how? Yeah, sure. Whatever. Just take the antiderivative of these t's with respect to t. Think of it as like a velocity that you're taking an antiderivative of to get position. Nope. If this is 0 to 1, you would take the antiderivative and plug in 0 and 1. Okay? So, be wary on your test. There will be a question where you will think, oh, I got to antiderive using the chain rule. You can't. You would divide by x, yeah. Now, last thing, quotient. It's important to talk about quotient because sometimes the best approach is to simplify, dividing everything by x. Okay, I get this. Now I can just take the antiderivative. That's plus x plus 3 log x. Yeah, the log thing. 1 over x is antiderivative is 1 over x. We haven't seen many logs, right? Kind of disappeared on us. If I had numbers, I would then plug in the numbers. 2, then 1. Just because of the domain restriction. It doesn't have to be because we're talking about 1 to 2 here, so we actually wouldn't have to worry about it, but yeah. I just threw it in there.
Putting the restrictions at the end like that, like that's like your answer, like that's good?
No.
Oh, you would have to.
If I ask you to find this, called the definite integral, I'd ask you to get the exact numerical value, like as much as you can, you know? So I would get 2 plus 2 plus 3 log 2 minus 1/2 plus 1 plus 3 log 1. The natural log of 1 is 0. So 4 plus 3 log 2 minus 3/2. That's 2.5 plus 3 log 2. That's the answer. Got it? Okay. Now, remember, when you subtract, the C will subtract and go away. Now, remember, power rule works. Pay attention to the less than now, so that you know what you're doing. Power rule works for any power, except the negative first power. If this is a negative second power, I'd have 2x plus 3 to the negative first, I'd have a negative 1, and I'd have a 1/2 to undo that inside. You could use U-Substitution to get that negative 1/2 if you wanted to, plus D. But the negative first power The antiderivative is log absolute. You have a 1/3 to undo. You could use U-substitution to get that 1/3. Or you just kind of figured it out, we've done it before. Now, here comes the last thing from our notes. We have a composition over here on the right, but it's invisible. The composition is the first power in the denominator. How do I know that this is a composition? Well, if I took the derivative of this, it's x. The antiderivative of this, conceptually, is log x squared plus 5. Now, okay, if I took the derivative of this, I'd have 1 over x squared plus 5 times 2x. I don't want 2x, I need 3x. So I'm going to need to multiply this by 3/2. Wait. Say you didn't get that. Here's where U-substitution might really help you. Set U equal to the entire denominator, which is the inside of the composition. Do the U-substitution method. Cancel and simplify and rewrite. This becomes 3/2 times 1 over U du. Take the antiderivative, there's that 3/2. Final thing that I will talk about is getting exact answers for these, but without using functions. And I'm going to spend like 2 minutes just to finish this video for the lesson. And you guys can go if you want to. The goal is to take the antiderivative of this, plug in 1 and 3, you're given the graph of f. You could use U-substitution or not. If you don't use U-substitution, you take the antiderivative of the outside, leave the inside alone, understand you need a 1/2 in front. Plug in 1 and 3. What happens? 1/2 f of 6 minus 1/2 f of 1. F of 6 is a value I can find. This is the graph of f. F of 6 is that y-coordinate. F of 1 is that y-coordinate. F of 6 is -1. F of 1 ends up being up 1 over 2, up 1/2 over 1, 1.5, or 3/2.
Sometimes I feel like after you teach, I can teach the lesson myself, but sometimes I feel like I wish you were a YouTube video and I could put you on 0.5 speed.
0.5 speed?
Yeah.
I need to slow down.
Yeah.
For you? Oh,
Yeah.
that's concerning.
Oh, yeah.
I don't know.
Well, that's why I have the recording of the video so you can go back and rewatch.
I think it was on the order. I got it in 3 though.
If I were to do this all at once, take the antiderivative of the outside, leave the inside. If I took the derivative of x squared to be 2x, I don't want a 2x, I just want x. I need a 1/2. Plugging in 1 and 2, I get 1/2 f of 4 minus 1/2 f of 1. F of 4 is 2.
Thank you.
F of 1 is 3/2. I get 1/4. And it's the same for these. You got to know the antiderivative of this is just e to the f of x. If you took the derivative of this, it would be e to the f of x times f prime. Plug in 1 and 5. The antiderivative of this is log absolute f of x. Now for these, you have to figure out what is f of 5. What is f of 1? F of 5 is 0. F of 1 is 3/2. That's my answer. Same would go for that. Okay?